All right. So, welcome to today's lesson on kinetics and collision theory, in which we're going to start to explore the the methods, and the speed with which reactions occur. This is going to be a departure from looking at the thermodynamics and what we call the spontaneity. This is a different thing entirely. So, the rate of a reaction can be determined by the rate at which the reactants disappear because they're being used up, or the products appear and they're being formed. And we're going to measure this as a change in the concentration. You can use pressure too if you're using gases, but concentration is an easier one to think about. The concentration with a change in time. So the rate is always going to be something with respect to a change in time, like a speed is a change in distance with a change in time. In this case, we're going to look at the concentrations of the products. Remember that square bracket, the A, if you put A inside that square bracket, that means the concentration of whatever inside. The concentration of A, and we're going to say in moles per liter or molar. So the change in the concentration of the products with a change in time, that's like a y over x down below. We're going to see delta y over delta x, which we'll see down below, or a change in the concentration of the reactants. But we're going to have a negative in front of there because we want to make this positive, because as the reaction proceeds, the reactants are decreasing, the concentration of the reactants are decreasing, and so we get a negative slope, and we want to keep that slope positive. Meanwhile, the concentration of the products are increasing, and so that will give us a positive slope. In this diagram to the right, I am showing a reaction as we're taking two N2O5 molecules and we're decomposing it into four NO2s and one oxygen. And we're going to start the reaction with 0.02 molar of the N2O5. And as many reactions start with 0 of the products, that's not always going to be the case, and we'll see that in the next unit. So as the reaction proceeds, the concentration, you can see the concentration of the reactants decreasing, and you can measure the rate by essentially finding the concentrations at any two times. In this point, we're going to say between 300 and 400 seconds. We're going to measure the concentrations of the N2O5. You can do this spectroscopically, like we did with Beer's law. There are other ways of doing it as well. And we're going to find that, indeed, we have a negative slope, negative 1.9 times 10 to the minus 5, and the units on the slope are on the rate is in molar per second, concentration divided by time. Now, you can see that as the concentration of the reactants goes down, the concentration of the products is coming up, and so the green line here is going to represent the concentration of the NO2. And because of stoichiometry, we're going to make 4 NO2s for every 2 N2O5s that we use up. And so we should get a rate for the NO2, which is twice the rate of the N2O5. And in fact, if we look at the NO2 between 300 and 400 seconds, keeping it at the same point, we're going to see that that change is in fact about twice the change in the N2O5. Finally, for the oxygen has a coefficient of 1, so we should have a 1/2 ratio there. And here's oxygen down here in the red, and between 300 and 400 seconds, we do get a rate. That's about half that rate of the N2O5. Now, in addition to the stoichiometry there, we also notice that as the reaction goes on, the slopes are getting smaller. Notice that when we come out to 600 to 700 seconds, coming out here, the slope now comes down to 2.2 times 10 to the minus 5 molar per second for the NO2. So we're getting a decrease in the rate of the reaction. So the rate decreases with time, since the rate depends on the concentration, and we'll talk more about this next lesson. The concentration or concentrations of the reactants. Now, we only have one reactant here, so there's only one to worry about, but we are going to see other reactions in which we have more than one reactant. So the concentrations of the reactants. So that's just how to think about rates. Now, how do we think about reactions occurring? That comes to us from something called collision theory. And collision theory tells us that in order to have a reaction, reactants must collide. Makes sense. We're talking about collision theory. And collisions, you can kind of think about this as, I mean, you're taking driver's ed, a lot of you now, or have been taking it, and you're trying to avoid accidents in which you have collisions, and those collisions will alter the car, and hopefully you avoid those collisions and you avoid any alterations, avoid any reactions. So molecules also have to collide for a reaction to occur, but that's not enough. You need to collide, but you need to collide with enough energy and the correct orientation. Now, the orientation is something that we can't control. It's random. And in fact, it's one of the things that reduces the rate of the reaction, because not all collisions have the correct orientation. Very few do. In the reaction you see below, I've got this OH, the hydroxide is coming into CH3Br, and it has to come in this specific orientation. If it collides in any other orientation, then no reaction is going to occur. The energy, though, is something we can control, and we can think about it, and we can illustrate it by modifying our potential energy diagram. So we have the enthalpy here on the y-axis. Remember, that's also the potential energy, excuse me, of our reaction. So the activation energy, the energy needed, is called the activation energy. And the way we're going to show it here is by sandwiching it in between the delta H of the reaction. So enthalpy is delta H. We can also have delta G. We could put a delta G. Let's put those little knots on there. But that only addresses the potential energy of the products and the reactants. That's not the whole story. So the reaction depends on that activation energy. And the activation energy turns out to be the minimum energy. As long as you have more, you're okay as well. Minimum energy that reacting particles for a reaction to occur. And the way we're going to put that in is by an increase in energy. Now, the energy that we need is coming from the need to break some bonds. We have to break some reactant bonds. And if you'll recall from our lesson on that, breaking reactant bonds is endothermic. And so you're always going to see this increase in energy from your reactants coming up to this other chemical here. I'll talk about what that is in a few moments. Where did my diagram go? I hate when that happens. We're going to find it later on, somewhere down on the document. All right, so we have this increase. This increase here, this is the activation energy, E sub A. And you can draw it there, or you can also draw it here. Either way. And it's always an arrow pointing up because it's indicating that we have to get up to that high energy. Now, once we get up to that point, then we can complete the reaction. And to complete the reaction, we're going to come down to our product. And I like to draw a nice smooth curve like this. Other people draw a more jagged kind of curve. It doesn't matter. As long as you've got that activation energy in there. And this decrease in energy now is the formation of the product bonds. And remember, forming bonds is always exothermic. We see the delta H of the reaction on here, and we could actually draw in, if we wanted to, where our potential energy, what the diagram, what the values were. I don't know the exact values. I think we're at negative 70 kilojoules per mole here, and I think we're at positive 40 kilojoules per mole here. And we're going to label some curves later on with more specific numbers. All right, so the reaction is proceeding in the forward direction, and the thing that occurs up at the top, before I get to that, the energy, that activation energy, comes from the kinetic energy of the particles. They have enough speed, they have enough temperature. Remember, kinetic energy measures temperature. Or if there's not enough energy, you can get a reaction started by using a spark or a flame, and that's where the burning of the wood, that very spontaneous burning of wood with a very negative delta G, comes into play. You need to put a little energy in, and once you get that energy in, the energy that it generates from the reaction keeps the reaction going. But you need to start it with that spark or the flame, and that's the activation energy. Now, that chemical thing at the top, chemical species at the top, is called an activated complex or transition state. So we can have it listed as a cartoon like that, or we can write it as such: HO, the blue is O, the red is H, HO, CH3, and the purple is bromine. And the dotted lines here in this activated complex are showing that we're breaking the bonds for the reactant, and we're forming the bonds for the product. But what the activated complex is, it's a high energy species that is a combination of the reactant, or reactants, and the products. And again, we're breaking reactant bonds, and that's the endothermic part, and we're forming product bonds, and that's the exothermic part. Sometimes we'll put, again, I hate when that happens, we'll put a little dagger, double dagger on that. That is the chemical symbol for an activated complex. And we're going to know that this is an unstable and temporary complex. You can't collect it. You can't put it in a bottle. But you can see evidence spectroscopically. So again, using techniques like Beer's law and some more sophisticated techniques. These things have a lifetime that lasts in the trillions or even smaller seconds. And so a lot of chemical research goes into getting very, very fast spectroscopy techniques so that you can actually see the bonds being broken and the bonds being formed. The other thing about the activated complex, it's the highest energy state up there. But getting up to the activated complex is not a guarantee that you're going to form products. In fact, it's a 50-50 proposition. 50% of the time you will form the products, but this is a reversible reaction, and 50% of the time you go back and reform the products. So I'm just going to draw in the diagram here an arrow to the right and an arrow to the left, showing that this reaction can go in either direction. So on the next page, we're going to look at this reaction in the other direction because there's a couple of features I want you to see. So we're turning this around, and what were the products are now the reactants. So there's the methanol and the bromide, and what was the product? Well, reactants are now the products, and we're going in the reverse direction. So if we draw in the curve, we'll come up to the top, and so this should look kind of backwards to what you saw before. The delta H of the reaction, here's the delta H. Now the delta H of the reaction is positive rather than negative, so this is an endothermic reaction. And the activation energy the activation energy has changed as well. The activation energy isn't from the highest product or reactant, it's always from the reactants. And so the activation energy, let's draw in the line here, the activation energy goes from the reactants all the way up to the top. And we could have drawn it inside there as well. Now that's the activation energy. This is for the reverse reaction. That was the activation energy just for the forward reaction. And now you can see that there's a relationship for a reaction that starts off as exothermic. The activation energy in the reverse direction is always going to be larger, and it's going to be larger because it's got the delta H of the reaction added to the activation energy in the forward direction. And this is going to have implications for the speeds at which reactions occur as well, because the reaction rate actually depends on the size of the activation energy. The higher the activation energy, the more energy you need. So higher EA means more energy is needed. And at a given temperature, there are fewer molecules, MLCLS, with the needed kinetic energy, and so the reaction is slower. And we will delve more into this in the next lesson. So in the next example, I'm going to give you something like what you're going to be doing on the homework. I'll give you a reaction. In this case, we got two BRNOs, not even sure what to call that, reacting to form two NOs and Br2 together. And I tell you that the delta H of the reaction is negative 100 kilojoules per mole. The activation energy is 50 kilojoules per mole. And I want you to draw and label the reaction energy diagram. By the way, notice that orientation-wise, the two bromines here have to come together because we need to be able to form that bromine-bromine bond. If the two bromines do not come into contact, and I don't know if it has to be exactly like this, parallel to each other, but if they do not come into contact, then this reaction won't occur, and the molecules will bounce off without a reaction happening. All right, so this is an exothermic reaction, which means we know that we're going to start with a higher reactants, and so you want to leave yourself some room here. So what I'm going to do is, since I know that my products are going to be down here, let's put the products in first. You don't have to do it, but it helps. The products with the Br2 and the 2NO. Now, since the reaction is exothermic, let's make that negative 100 kilojoules per mole. Then let's put our reactants up here at 0. It's just an arbitrary 0. You could call it 200 if you wanted. Just make sure that the numbers match in terms of what your delta H is. And here's our delta H of the reaction coming down here. So it can be, you can put it anywhere that makes sense when you put in the delta H. So when I say you want to label it with the delta H, and you want to label, we got to put in our two BRNOs here. And then we need the activation energy. Now the activation energy we said was up at 50. Now that's always a positive number relative to where you're starting. So that's going to come up at 50. And I'm going to put a little dot there, like halfway in between my products and my reactants, just to show coming up and going down. And my activation energy then, here's my EA, going to label that. Or if you want to, you only have to label it once. You can label it out here as well, as long as you see that EA coming up from the reactants. All right, so that's our lesson for today, and I hope you're all doing well. The homework will follow this, and I will see you next time in class.